Next, I want to talk about symmetry. And we can use symmetry to help us with graphing. In the last example, we just used plotting points. And then if you continue that table, you would have realized that the values were repeating. But you wouldn't know that necessarily unless you started plugging things in and you recognize that it was repeating. You could have used a test for symmetry there to actually show that it was symmetric with the polar or x-axis. And that helps as well. So here I'm going to talk a little bit about that symmetry idea. So there's three kinds of symmetry we're going to talk about for polar equations. The first is with the polar, or what we're used to as the x-axis. So you have the same symmetry above and below. And, if you look back to our example here, you did see that, right? You had that same symmetry above and below. So to test for something like this, what you do is you replace theta with negative theta, and you see if you get the same equation back out. And if you do, you know that you definitely have that polar axis symmetry. The second kind of symmetry that we see is this with respect to the line theta equals pi over 2. So what happens is here's your line, and you can see that you have this sort of kind of a different kind of symmetry here, right? It's just not an up and down, it's a left to right symmetry in a way. So we replace the r theta with negative r negative theta. And again, if you get the same equation back out, then you do have symmetry with respect to the line theta equals pi over 2. So again, you sort of have, again, different kind of symmetry here. It'd be like the y-axis symmetry that we're used to. So you have this kind of left-right symmetry instead. And then the third one is what we're used to seeing with the origin. So that kind of diagonal symmetry. And you can check for that by replacing r with negative r. And again, if you get the same equation back out once you simplify, you would have that diagonal symmetry, that symmetry with respect to the pole or the origin. Now, the thing is, for polar equations, a little bit different. If you fail a symmetry test, you may or may not have that kind of symmetry. I know when we're used to the rectangular system, if you fail a symmetry test, you could say for sure it does not have that kind of symmetry. We can't totally rule that out here with polar, but we can tell us if we do see that we get that true statement in all of these, then we definitely have that symmetry. So that's what it's telling us. It's not telling us when we don't have symmetry, like we're used to seeing. It's telling us if we do, definitely in those cases. So let's keep this close by and let's do an example. So we're going to check for symmetry and then we'll graph as well. Now, just because you have symmetry, you will probably still have to create a table of points. But again, it just helps you so you know you don't have to find as many points, or you could recognize that symmetry a little bit faster. And that would have helped us with that last example too. We could have recognized that symmetry right away. And again, we can also see by repeating values, but it just helps us to have something else to look out for. So I'm going to check first for symmetry with respect to, so WRT stands for with respect to, and I use that on this page too in case that wasn't clear. So symmetry with respect to the different axes or things. So I'm just going to test in order. I'm going to test with the polar axis first. So I start with my original equation. And then if you go back to your steps on the page before, to check to see if you have the symmetry with the polar axis or like the x-axis, you replace theta with negative theta. I'm just going to use a different color just to show that change. Now here you have to recognize your rules. You want to remember that cosine is actually an even function. And because cosine is an even function, this is actually the same thing as cosine theta. So cosine of negative theta and cosine of theta are going to be the same exact thing. So notice how we got the original function. Or I should say equation here, not a function, equation. So yes, we have symmetry with respect to the polar axis. So I am going to notice that I do have that kind of up and down symmetry for this equation when I graph it. Now you can have more than one symmetry, or you could have no symmetry sometimes too. So you want to always check. So with respect to the line, theta equals pi over 2. So I start with the original equation. And then if I look for that one, I'm going to go here. And what you do is you replace both r and theta with their negative. So we change out both of them. And again, I'm trying to use color so you can see the specific changes for each type of symmetry. And again, you're going to clean it up. So one thing I'm going to notice, again, cosine is even. So this is the same thing as cosine of pi. Now I should have an r here, so let's divide by -1 on both sides, or multiply by -1 on both sides, and you get -1 plus cosine theta there, if I bring that negative to the other side. And if I look at this one and this one, those are not the same. The negative's in the wrong position, right? It's not the same as the original equation. So when this happens for polar equations, basically it just doesn't tell you anything. It doesn't tell you that there is symmetry. It doesn't tell you that there is not symmetry. It just says, hey, I don't know. So in this case, because we did not get the original, basically you may or may not have symmetry with respect to the line theta equals pi over 2. So it just doesn't tell us anything. So we're going to move on. And then the last one we looked at was like the origin idea. So that was the pole. And what I do for this one is I replace r with -r. Again, I should have just an r there. So if I multiply everything through by -1, what happens is I get r equals like I should have, but then it's -1 plus cosine theta. Again, the signs have switched. And this is not the same as the original equation. So again, it just doesn't tell us anything. There may be symmetry, there may not be. I just don't know definitely. So there may or may not be symmetry with respect to the pole. Okay, so we don't know. But the only thing I do know is I know I definitely have symmetry with the polar axis, or that x-axis. So I have this vertical symmetry going on here. So it's something to definitely watch out for. And actually, not to keep dwelling on this example that we already did, I can find it. Let's see. This one here, if we went to this equation and we tested for that polar axis symmetry, let's see if I can move down for a second. Where you just replace the theta with negative theta, you would see right away that because cosine's even, you get the same result. So you do have that symmetry with the polar or x-axis. All right, so at this point, I'm going to have to make a table. Now you want to remember that as you're making your tables, if you're doing cosine and sine, their period is 2 pi. So at the most you'll have to do is from 0 to 2 pi all the way around. But this one, like the last one, because we have that vertical symmetry, you're going to be able to stop at pi instead, because you're going to have the same values when you go down bottom. But again, if you're not sure, if you're kind of, I don't know what to do, you can always go through 0 to 2 pi and just double check all those values. And again, if there's repeats, you'll see the repeats automatically. Here, I know it's going to start repeating once I get after pi, like in my last example, because I have that vertical symmetry. All right, so we're going to just make a quick table again. So I'm going to do 0. I'm going to do pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. And again, the only reason I know I can stop at pi for sure this time is because of that vertical symmetry. So if I have that vertical symmetry, I only need to go through 0 to pi here. I'm gonna let you do these ones on your own. So you're just gonna plug things in, right? You're just gonna go 1 minus cosine of 0. So you'd have 1 minus 1, which equals 0. So you're going to go in and plug each of these in. When I do the second one, pi over 6, you end up with about 0.13. When I do pi over 3, I have 0.5. When I have pi over 2, I have 1. When I have 2 pi over 3, I have 1.5. When I have 5 pi over 6, I have about 1.87. And then when I have pi, I'm at 2. So I have 0, 0, about 0.13 pi over 6, 0.5 pi over 3, 1 pi over 2, 1.5, 2 pi over 3, about 1.87, 5 pi over 6, and then about 2 pi. And again, because we have that vertical symmetry, you're going to start seeing that repeat. Let me make a quick polar grid, and then of course I'll show you the nice picture in the book too. But okay, so we always start with 0, pi over 2, pi, and 3 pi over 2. And this is how I usually make it. So I usually do the halves first, half of each quarter. So this is your pi over 4. And then across from that is your 5 pi over 4. And then going this way, just going to do my best to cut that in half as well. You have 3 pi, and then down here you have 7 pi over 4. Now I do my pi over 6 angle. And again, I just bring it straight through, do my best to estimate here. So this is pi over 6. And then this would go ahead and be 7 pi over 6. And then I'll do my pi over 3 angle. And again, this is not perfectly to scale. And 4 pi over 3. So you just do the best you can. I know because we're doing this by hand, you should take out a protractor, obviously, and do that, but we can just do a rough sketch here. 2 pi over 3, and this is 5 pi over 3, and then one more. 5 pi over 6, and finally 11 pi over 6. Oops, 11 pi over 6. Okay. And I'm going to do out my circles. I'm going to do those in blue just to make it a little bit easier. So 1, 2, I'm just using the grids on my paper for my R's. 3. And let's start plotting these points. So I have my points. Okay. So I have 0, 0 to start. So that's going to be right here. And then my angle is pi over 6, excuse me. And I'm going out 0.13. So I'm just going out a little bit here, maybe like right here. And then my angle is pi over 3. I'm going out a half. So about right there. And then at pi over 2, I'm at the 1. At 2 pi over 3, I'm at 1.5. At 5 pi over 6, I'm at almost 2. And then at pi, I'm going to be at 2 exactly. Now, if you're having trouble with symmetry here, go ahead and fill in the rest of the values. You can do 7 pi over 6, 4 pi over 3, 3 pi over 2, 5 pi over 3, and 11 pi over 6. So do the same angles underneath, and that will give you those points there as well. Or you can note that you have symmetry here, and you have that up and down symmetry. So what I'm going to do is I'm just going to kind of mirror that point. So this point here is just pi over 3 above. So I'm going to pi over 3 below and keep the point the same. Okay. Here, again, I'm just going to kind of mirror it below. Right here. 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 Now, not the best picture, but we're going to go ahead and connect those points. Don't forget you started at 0, 0. So you're actually kind of going in and circling out and then back in again. Now, this is not quite a circle because it actually pokes in here at 0, 0. So let me show you what it looks like when you have technology and you're not just doing it by hand. It would look like this. So you can see there's your initial top half. We recognize that we have symmetry, the up and down symmetry, so we just mirror the image on the bottom. But again, if you don't like that, you can go in and just pick points and plug them in. You know your cosine and sine values at this point, or hopefully you have them easily accessible. And you can go ahead and find that. And this is what your finished picture looks like. All right, let's do one more example. Okay, so here's the example we're going to do next. So we're going to graph r equals 1 plus 2 sine theta. And first, before I start making a table, I am going to check for symmetry to see if there's anything helpful there. So I have the 3 forms of symmetry ready to go and set up. And again, I'm going to use a different color to show what we're changing. So to check for symmetry with the polar axis, which is that, that x-axis that we're used to, that kind of vertical symmetry there, we're going to replace theta with negative theta. Now, sine is not an even function like cosine was. So what happens is that negative doesn't necessarily go away here. So it actually can kind of just come out. So it's -2 sine of theta when you simplify. It's an odd function, so the negative just comes outside. And again, this is not the same as the original. So basically, again, we just don't know. So when you don't get the same as the original, it doesn't mean that there's not symmetry. It just means you don't know. There could be or there could not be. So the first one is not helpful for us. We tried the next one. So in the next one, we replace both r and theta with their negatives. And again here, this negative just kind of come out. Sine, again, is not an even function, so that negative remains. R should be negative, though. Sorry, R should not be negative, should be positive. So I'm going to multiply everything through by a -1. And I get -1 plus 2 sine of theta. Now, this is almost the same as the original, but not quite, right? That 1 becomes negative. So again, this is not the original. So we just don't know. Is there symmetry? I don't know. And then for the last one, we just replace the r. If I try to make the r positive and multiply everything through by -1, again, you can see that this is not the original. So I really have no idea if we have symmetry. So nothing helpful here about symmetry. We may or may not see some symmetry in our final result. So I'm going to have to go ahead and just start making a table of points. Now, my sine function is periodic with period 2 pi. I don't know anything about symmetry here, so I'm going to assume that I'm going to have to go all the way from 0 to 2 pi with my points and just keep plugging different points in. If I start to see repeats and stuff, a pattern, then I can stop. I don't see any patterns here with symmetry, so I have to be really careful there. But I'm going to start with thinking about 0 to 2 pi and just make a table of points. I'm going to do the usual 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. That's the usual from the first group. But if you look at your chart here, again, I don't know anything with the symmetry, so I should really keep going here to complete the circle. So I'm going to do 7 pi over 6. I'm going to do 4 pi over 3 and 3 pi over 2. And then I'm going to do 5 pi over 3 and 11 pi over 6 as well. Again, I'm picking values that I should already know the answers to for our sine and cosine. Right, these are ones that you should have values for. And then again, I'm back at the start with 2 pi. So I'm not going to do every single value. And You can try it at home and check your work. So I plug in 0 here, it'd be 1 plus 2 sine of 0 as you go through. And if you think about sine of 0, that's 0. 1 plus 0 is 1. So your first value there ends up just being 1. And we're going to go through for all of them. So for the next one, I would just plug in sine of pi over 6, and I would get out my sine chart, and I would keep simplifying all the way down. Now I'll save us some time here. This one simplifies to be 2. Here about 2.73. Excuse me. Here we have 3. Again, about 2.73. Now be careful, you're like, oh, I repeated, so maybe I'm done. Try the next one or two and make sure you see the same exact pattern before you stop. If I go to the next one, I get the value of 2 and I get the value of 1. So you can see that, you know, although I see some repeats, they're not in the same order, right? This is going backwards. So that's not repeating. It has to be the exact same pattern all the way down. So I'm going to keep going. When I plug in 7 pi over 6, I do get 0 there. Here I get negative 0.73 approximately. Here I get negative 1. I get another negative 0.73. And again, I know you see a little bit of repeat, but I'm not 100% sure yet just because I see one value. Next value is 0. And again, be careful. You say, oh, but there's a 0 and a 7.3, same thing. It's not going in the same order, right? This had 0 first and then negative 7.3. Then I had negative 7.3 and then 0. So that's not the same pattern. It's not repeating yet, even though some of the values are similar. And then I'm at 1. If I continued on from here, then I would see this exact same pattern coming along. So if you're not sure, don't just stop. You really need to be positive that you see repeats there in the correct order. So I would wait to see a couple in a row, maybe like 3 or 4 in a row, and then say, okay, this clearly is repeating, right? But make sure you're really confident there before you start stopping and thinking that you have a repeating part. If nothing else, you know that sine and cosine have period 2 pi. So for graphing sine and cosine polar equations, you know you can stop at 2 pi. So that's as long as you'd have to go at the most, again, unless you have something a little bit different. So I'm going to just bring in the text here because to graph this is really kind of difficult by hand. And I want to show you what happens. So here you have the first set of points up through pi plotted for you. And then for the next few points here, because your R value is negative, remember it reflects across. So that's why for the 4 pi over 3, you're not on this side, you're on the other side. That's because your R was negative, so it bumps it to the other side. And then same thing for 3 pi over 2. Again, you're not on this side because your R is negative, so that's why you're up here at negative 1. So you sort of have this little kind of circle or spiral starting. And then if I finish, again, that negative on the 5 pi over 3 is going to bump it to the other side. And then I have 0, and now I'm back at 1. So you actually create this little mini loop in the circle here with this polar equation. So this is what your final graph looks like. And then after here, we'll just keep looping around over and over again, the same pattern. It's kind of outer circle, inner loop over and over. But that would be our picture there. All right, so let me just wrap up these type of graphs for a second here. We talked about how we get circles. So this is something called a limacon, this shape. So it means snail in French. So I don't know if it really looks like a snail, but I guess it's kind of has that snailish shape to it. So it's called a limacon. And they look like this. So your equations could look like R equals A plus B sine theta. R equals A minus B sine theta. Or you could have R equals A plus B cosine theta. Or R equals A minus B sine theta. And A is at least 0 and is at least 0. And what happens is, the ratio A over B is actually what determines the lemmason's shape. So for instance, and bear with me on these pictures here, if your A over B is less than 1, you end up having that inner loop like we just saw. Now, it doesn't have to be this direction, right? We saw it in a different direction. But you sort of, let's see if I can actually draw this. Have something like that. So you have an inner loop, which is like the one we just saw. We had that inner loop picture. If your A over B equals 1 exactly, then what happens is you have a heart shape. These are actually called cardioids. So it kind of looks like this. Kind of looks like I guess like a kidney bean, also like a lima bean or something like that. But they're called cardioids. They're heart-shaped. If your A over B is between 1 and 2, it is what we call dimpled, but there's no loop. So it's kind of got that kidney shape with just like a little dimpling. Goes in just like a little bit there, but there's no loop. This one here has a full kind of full dimple, heart shape. And then the last one, I'm running out of room here, but I'm gonna see if I can just sneak it in down the bottom, is if your A over B is at least 2, you have no dimple and no inner loop. So I don't know, it kind of looks like a little flatter, I guess, on that side, maybe. So it looks very oval shape, but maybe just a little bit flatter here on this side instead. And again, I'm going to show you the text just to make it a little bit easier. So those are your 4 shapes. So a clear loop. Here you have a heart shape. Here you have a little dimple. So it does go in a little bit. And here you don't have any dimple. It looks kind of more straightish, but it's not a perfect circle. So that is important to note there. All right, so those are your lemmasons.